In this lesson, we'll talk about permutations and combinations. Permutations and combinations are the ways of counting certain arrangements or sets. The branch of mathematics that studies counting techniques is called combinatorics. The fundamental counting principle tells us that if a task involves a sequence of k choices, and if ni is a number of ways that ith choice can be made, for I being any number from 1 to k, then the number of ways that the task involving all k choices can be performed is the product of the number of ways that the task can be performed for every particular choice I. Let's see how this fundamental counting principle works with this particular word problem. Next semester, you're going to take one science class, one math class, one history class, and one English class. Well, so there's 4 types of classes. According to the schedule, you have 4 different science classes, 3 different math classes, 2 different history classes, and 3 different English classes to choose from. Assuming no scheduling conflicts, how many different 4-course selections can you make? Okay, let's N1 represents the number of ways you can choose a science class. So what's N1? Well, there's 4 different science classes. Therefore, N1 equals 4. Let N2 represents the number of ways you can choose a math class. Well, this is 3 possibilities because there's 3 different math classes offered. So N2 is 3. And so on. Let's N3 represents the number of ways we can choose a history class. So N3 is 2. And finally, N4 will be the number of ways you can choose an English class. So N4 is 3. Therefore, the number of different 4-course selections is the product of those ni's from 1 to 4. So it's really 4 times 3 times 2 times 3. And when we calculate this, it becomes 8 times 9, so it's 72 course selections. So we have a lot of choices, 72 ways. A permutation of a set of n objects is an ordered arrangement, a sequence of these objects. So for example, if we have 3 objects, 1, 2, 3, then we can list following sequences. It could be 1, 2, 3 in that order. It could be 1, 3, 2. So both of these sequences start with 1. Now we can start with 2 and do the same, interchange the last 2 numbers, so 2, 1, 3, or 2, 3, 1. And finally we can start with 3 and interchange the other 2 numbers, 1 and 2, or 3 and 2, 1. So as you see, we have 6 permutations, 6 different arrangements, different sequences. So remember that permutation is a sequence, so the order of numbers really matters. And the number of permutations of n different objects is calculated as n factorial. This number of permutations could be denoted as p of n objects out of n available objects. So let's see how this definition can be applied to our previous example of permutations of 3 objects. Well, on the first place, we could use either 1 or 2 or 3. So the first number was chosen in 3 different ways. The second number, if we already have the first, we have only two possible choices. On the second place, we could use either 2 or 3. So those are the two choices, times 2. And obviously the third number is already determined because we already used the first two, so the third one is whatever's left over, so it's just 1. Okay, that works like 3 factorial. So yes, we have a confirmation here. This formula works in our example. And here we have a picture of a cube with permutations of 4 numbers written on every face by their edges. Since we have 6 faces and each face has 4 edges, so 6 times 4 is 24. And yes, if you use 4 factorial to describe the number of permutations of 4 objects, we have exactly 24. So as you see, we could assign different permutation for each face and each edge. We can probably notice some other properties of this cube. For example, as you see, this corner has 4 on each side, and the permutations that are written along those edges either start or end on 4. So the 4 is the closest to this vertex. The same is with 1. So it's a very special arrangement. In how many different ways can 5 instructors be assigned to teach 5 different classes, providing that each instructor teaches exactly one class? Okay, so we have 5 classes. Let's say those are our classes, 1, 2, 3, 4, 5. And then we assign teachers. The teachers will be marked from 1 to 5 as well. So in how many ways we can assign 5 teachers to the first class? Well, it's in 5. Well, since it's 5 teachers, then each of them could teach this class. Therefore, there's 5 choices. But if one of those teachers is already assigned to teach this first class, there's only 4 left over to be assigned to teach, for example, the second class. So there's 4 choices here. And since we already assigned 2 teachers, there's only 3 teachers that could be assigned to teach the third class. So there's 3 choices here. And so on. The remaining 2 teachers could be assigned in 2 different ways to teach the following class. And finally, if we have already assigned 4 teachers, the 5th one must teach the last class. So those are the ways to assign teachers to each class. And from fundamental principle of counting, we need to multiply those ways. So altogether, we really end up with 5 factorial. This is the same as arranging 5 teachers in a sequence of length 5. How many sequences of length 5 would it be? Well, this is a permutation of 5 elements out of 5 possible. So it is indeed 5 factorial. And how much is 5 factorial? Well, we can either calculate this by hand or use your calculator, and when you push the button Math, scroll to Probability and use number 4 for factorial. That becomes 120 ways. Okay, so if we have n objects and we take permutations of all n objects, the number of such permutations will be n factorial. However, if we have n objects but we're taking only k out of them at a time and permute them, so such number of permutations will be denoted p of nk, and the formula for the number of those permutations will be n factorial divided by n minus k factorial. Why? Because this n factorial corresponds to all permutations from 1 to n. So let's say if n is 5, like in the previous example, it will be 5 times 4 times 3 times 2 times 1. But if we are taking only 3 places to fill it up, let's say we would like to calculate p of 5 choose 3, then only the first 3 places are important. The last 2 will have to be forgotten. So what we do, we're trying to cancel this part, therefore we divide by 2 times 1, which really means that we are taking 5 factorial and dividing by 5 minus 3 factorial, which is 2 factorial. And in this case, that becomes 20 times 3 is 60. So there's 60 ways of permuting 3 objects out of 5 possible objects. Generally, if we list the product from 1 to n and then divide by the number of permutations of those elements that are not taken, and the number of not taken elements is n minus k, then we obtain all the possible ways of permuting the k objects out of n possible objects. Notice then your calculator will have different notation. The p of nk is actually recorded as npk, which means permutations of k objects out of n. With 6 different flags, how many different signals can be sent by placing 3 flags, one above the other, on a flagpole? So what we have here, we need to choose 3 flags out of 6 possible and arrange them in order. So the arrangement is important. Therefore, we're talking about permutations, and those will be permutations out of 6 possible. We are choosing 3 flags. So 6p3. We can calculate this directly from the formula, or we can use a calculator. So from the formula, it will be 6 factorial over 6 minus 3, which is 3 factorial. That's not too difficult, because when we cancel the 3 factorial, what's left is actually 4 times 5 times 6. So it's not too large number. 20 times 6 is 120. 120 different signals can be sent with these flags. If we talk about sets of k objects, where order is not important, this will be called a combination. Combination of k objects is a set of those objects, not a sequence. So if we have k particular objects, there's only one combination that can be made out of them. However, if we have n overall objects and we are choosing k at a time, then the number of such combinations, that means sets of k objects out of n objects, is denoted C of nk, C for combinations, and the number of those combinations is given in this formula. It is n factorial over n minus k factorial, so remember this part of the formula really represents the permutations, k objects out of n possible. So this part of the formula represents the number of all possible sequences of k objects out of n. However, since we don't care about the order of those sequences, we divide this by k factorial, by number of permutations of those objects in a set. So, as we notice, the combinations of k elements out of n is the same as number of permutations of k elements out of n, but divided by k factorial. Since the order is not important, there is less combinations than permutations of the same size. This equation can be seen equivalently if we multiply the combinations by k factorial, we obtain the permutations. Also, we have another notation for combinations. This is called Newton bracket. So instead of C of nk, we write n over k, and we read this n choose k in a bracket. There's no division bar, so it's not a fraction. It's called a Newton bracket, and you read this n choose k. This also represents combinations of k elements out of n. So this really gives us the number of possible sets of size k that we can create out of n objects. Let's evaluate C of 10 choose 7 and P of 10 choose 7 without a calculator. That means by using the formulas that we've seen. So C of 10 choose 7 is the same as n factorial, so it's 10 factorial, divided by k, that is 7 factorial, times 10 minus 7 factorial. Okay, so if we reduce the 7 factorial with 10 factorial, what's left is 8 times 9 times 10 in the numerator, and over here we have 3 factorial, which is 1 times 2 times 3. Now we can reduce the 3 with the 9 and the 2 with the 8, for example, and we end up with 120 ways. So 120 combinations of 7 objects out of 10. Okay, let's calculate permutations. Permutations are just n factorial, which is 10 factorial, divided by n minus k, so it's 10 minus 7 divided by 3 factorial. So this is quite a lot, because it will be like 4 times 5 times 6 times 7 times 8 times 9 times 10. And when you use calculator, that turns out to be 604,800, a lot more than 120. And you can check that this is the same as 120 times 7 factorial. Check using your calculator, it should be the same. In the B exercise, we want to confirm that these numbers are correct just by using calculator. And on the calculator, you will have this notation, as we mentioned before. So let's see how this can be found on the calculator. To calculate the number of combinations of 10, choose 7, we write 10 and then math, scroll to probability, go into combinations number 3, and 7 equals, enter, and we have 120. And to find out number of permutations, we go similar way, 10, math, scroll to probability, number 2, permutations, and 7 equals. So it's 604,800. Okay, so we've got number of combinations 7 out of 10 is 120, and number of permutations 7 out of 10 is 604,800. Now consider 8 points such that no 3 of them are collinear. How many triangles can be formed using the given points as vertices? Since no 3 of the points are collinear, that every choice of 3 points will give us a triangle. Therefore, the number of all triangles formed by these points is the number of all possible sets of 3 points out of 8. So it's really a number of combinations of 3 points out of 8. As we mentioned before, this could be written in a form of a Newton bracket, just 8 choose 3, number of combinations. And the formula is as above. So it's 8 factorial over 3 factorial, and 8 minus 3 is 5 factorial. After reducing 5 with 8 factorial, we end up with 6 times 7 times 8 in the numerator and 2 times 3 in the denominator, which cancels with the 6, and the overall number of all different triangles is 56. Again, you could plug it in this to the calculator and you will get the answer 56 as well. So I wish that you will be able to do both calculator and for small numbers using this formula, because that's the way that you get familiar with it. A committee of 3 men and 2 women is to be selected from a group of 12 men and 8 women. Determine the number of different ways of selecting the committee. Well, we have 2 categories. We need to select 3 men out of the group of 12 men. So the number of such selections will be 12 choose 3, because the order is not important. What's important is just the set of 3 men. And then we need to select 2 women out of the group of 8 women. So that's another combination. We need to choose 2 out of 8. And using the fundamental principle of counting, we need to multiply these 2 number of ways of choosing 2 different categories of people, and then calculate. We can even use calculator. Please do it on your own. So those are combinations. You push the button math, then probability, and for combination will be number 3. So altogether you should end up with 6,160 ways. A committee is going to select 30 students from a pool of 1,000 to receive scholarships. How many ways could the students be selected if each scholarship is worth the same amount? Well, we need to select basically just 30 students out of 1,000. So it's 1,000 choose 30, written either this way or that way. Combinations, choose 30. Use your calculator, and that turned out to be approximately, because that's a very large number, so we can just approximate it, 2.4 times 10 to the 57. Wow, that's a lot of ways. However, if each scholarship is worth different amount, oh, that's different story. We need to arrange those scholarships, let's say from the highest amount to the lowest amount, which really means we're talking about permutations because the order is important. So we are choosing the first person out of the 1,000 in 1,000 ways. Then we're choosing the second in 999 ways, and so on. Therefore, this is really calculating the permutation, choosing 30 students out of 1,000 possible students. And then again, if you use calculator, this turned out to be approximately 6.4 times 10 to the 89. So this time it's even more possible choices, a lot more. And the last example, in how many different ways can 6 people sit by a round table? Well, this time, if we'll talk about in how many different ways we can place 6 people in a line, then we'll talk about permutations. That will be just 6 factorial. Let's say 1, 2, 3, 4, 5, 6 in a line. However, if we connect the last point of this segment to the first point and make it a circle, the permutation of the type 1, 2, 3, 4, 5, 6 will actually be the same as the permutation of the type 2, 3, 4, 5, 6, 1, because we can rotate around the table, and these two ways, when online, they will actually be the same when on the circle. Let's say the first arrangement could be like this: 1, 2, 3, 4, 5, 6. But if all these people will rotate either 1 or 2 or 3 or 4 or 5 or 6 places, all of them the same way, then the new arrangement will actually be considered to be the same, because the arrangement that the 1 starts from here, and then 2, and then 3, and 4, and 5, and 6, is actually considered to be the same. And if we move the 1 to the different spot, it will still be the same, because what matters here in a round table is what are the neighbors of the particular person. It doesn't really matter where we start. Therefore, every 6 permutations will have to be considered as one and the same. So we need to divide the 6 factorial by 6, and we end up with just 5 factorial. So as soon as we place the first person, the rest of them can permute to create different permutations, but not the first one. Therefore, it's actually 5 factorial, not 6 factorial.